Okay, hello everyone, and welcome to today's lecture. My name is Ellie, and we have a lot of exciting content to get through today. So, our lecture is provided by ATAR Notes, who provide resources for high school students. Those resources include study notes, lectures, discussions, videos, newsletters, the infamous ATAR calculator, articles, and heaps more. So, let's get into today's lecture. Today we're going through a revision of specialist content that will be useful for you coming into your externals and your mock period. All right. So as you can see here, this is a list of the main content that you've gone through in Unit 3 and 4 broadly. So today we're going to be going over those last two topics there, rates of change in differential equations and statistical interference. All right. So I know personally, those last two topics were probably the ones that I found the most confusing when I was in specialist. Um, so it really will be good for us to get through them. I know I particularly also had trouble with the complex numbers as well. Those ones are a little bit tricky. So I completely understand the struggle that you guys are going through, especially coming into your external and your mock period. There's such a wide breadth of specialist content, kind of as opposed to methods where it's mostly just focused on, calculus and then the statistics at the end. In specialist, we focus on so many different things that it can be kind of quite overwhelming to do revision from content from, that you learned a year ago, when it's quite different. So I completely understand the struggle. That's why we're going to be going over those last two topics today in quite a bit of detail. I'll just give you guys a quick rundown of the structure for today. So we'll go over modeling motion, then we'll go over statistical interference, and within that, sample means and confidence intervals. And then right at the end, I'll give you guys some external exam advice, particularly from somebody who, as I said before, got through specialist in one piece. I have plenty of tips for you guys. So just a few announcements. The slides are also available for download if you want to save those just to help you with your notes, anything like that. This is a recorded lecture. It's 2 hours long. So there's a live chat if you have any questions, either about the content we're going through, any content we're not covering today, like prefine induction, complex numbers, any of that kind of thing. If you have any questions about myself or study tips or anything like that, those questions are also welcome. I've had a few questions in the past about whether you can download these lectures and you can't, but what I would recommend is for you to save the link because you can come back to the recorded lecture anytime that you'd like. Just save the link and you can come back really easily. Okay. So before we get into it, just a little bit about myself. So I graduated in 2021. I'm currently studying law and economics at UQ. I got an ATAR of 99.55 and my overall score in specialist was 96. So I'll go over a little bit in the final section on advice, just kind of about how I got this score, but just for a brief bit of background, the majority of those marks that I lost was in the external. So I went into the external with 49 out of 50, so I lost 1 mark in one of the exams. And then in the external, I lost 3 marks. But to be completely honest, that is kind of to be expected. So the reason that I lost those 3 marks in the external was primarily because I dismissed some of the syllabus dot points, to be perfectly honest with you. So just before we even get into the content, just to learn from my mistakes, especially if you guys are like really wanting to do well, you want to get into like med or law or engineering or something that's like quite high level, and you really need to get just like a very astronomically high score, just specifically for specialists because there's such a wide breadth of content. Do not disregard any of the syllabus dot points. So what you should be doing is going through the syllabus, making sure there isn't anything you've missed, and also don't necessarily take the questions that have been asked in previous externals as the law of the land. All right, go through each of the syllabus dot points and make sure you've practiced complex questions for each of those syllabus dot points. Because for myself, in the specialist exam, so in the 2021 exam that I sat, there was a particular question about polynomials and matrices. It was in the paper 2, if you guys want to actually look at it. But it's I wasn't prepared for it, and it really was quite an easy question when you had a look at the answer. And in fact, when my friends and I walked out of the exam, we went, "Oh, that's how you do it." Um, but just making sure that you don't disregard any of those syllabus dot points because you think, "Oh, that will be easy." Make sure that you really actually focus on each of those individually. Make sure you're practicing complex questions for each of them. If you take nothing else away from this lecture, don't disregard any of the syllabus dot points, especially as well because there is such a wide breadth of content. It's really easy to kind of look at some of the dot points and be like, oh, do I really need to know that? Mm-mm. But please don't do that. Go through, make sure you know everything. Anyway, let's move on to the content for today, and I'll go over a few more study tips that I have at the end. All right, so let's start with modeling motion. So here is what the syllabus requires you to do. Firstly, you need to examine momentum, force, resultant force, action and reaction, and then consider constant and non-constant force. So we will go through these two in a little bit of detail. Just a quick tip in the box there is to have a look at the cognitive verbs. And the definitions of those are also available under definitions on the QCEE website. So make sure you understand they're all underlined here. This is less so for specialists, more so for the sciencey subjects, but it is, like physics, bio and chem, but it is still useful to understand and know. All right, let's get into momentum and forces. So momentum is mass multiplied by velocity, all right? You can think about momentum as the force or the ability to exert force that an object has when it is moving, right? So think about a flying bird that flies into your window as you're sitting at your desk, right? And it has mass, it's flying, so it has a certain velocity. It crashes into your window, and because of that momentum that it had, it cracks your window, all right? So that's how you can think about momentum. It's the force that something has as a result of it having mass and moving. Alright? So, force is the rate of change of momentum in a system. Alright? So dp dt. Alright? And we also know that force is equal to mass multiplied by acceleration, which is also known as one of Newton's laws. Alright, so hopefully you have seen that one before. The the F equals ma equation is really quite important getting into this topic in specialist. So make sure that you hold on to that one because it's not on your formula sheet. And something that I tend to see is when you're doing questions involving motion, a lot of the time if you're looking at a question and you really don't know where to go, it usually means that F equals ma is involved somehow. Alright, so not always, but especially if in a question you're given a value related to mass, it almost certainly means that F equals ma is involved somehow. So it's kind of easy to forget that one because it's not in your formula sheet, but make sure that you do hold on to that one because it just does come in quite a lot. The units for force is capital N or newtons. And then force, acceleration, velocity, and displacement are What that means for a student like yourself is that when you are answering questions involving force, acceleration, velocity, and displacement, it means you always need to include a direction. And if you don't include a direction, it usually means that you'll lose marks. So really watch out for that too. So say a question asks you to find the velocity of a particular, say the velocity of a ball, alright? A ball being thrown at a particular point. So if you just find the velocity, 5 meters per second, you'll lose marks because you need to find the direction of that velocity. A lot of the time it is just kind of like straight down or straight up or straight to the right or something like that, so you can just kind of write that and it's not too much of an issue. Sometimes though, you'll also need to find an angle as well. So say we have a ball being thrown and you need to find the velocity of the ball as it hits the ground. You will also need to find the angle that the ball hits the ground at. So whether it hits it like almost vertically or like more of an angle like this, you'll need to find that angle too. So make sure you put in your notes to make sure that when you're dealing with vector quantities, always remember to include a direction. Otherwise, you'll lose marks for forgetting them, alright? Because direction makes up part of these vector quantities. Alright. Next, the definitions that we went over just before aren't wrong, but they're not super practical by themselves. They're not super useful for the content that we're doing in Specialist. And that's because going through Specialist, we actually have a look at forces that are acting all at once. So lots of different forces, lots of different strengths, acting at lots of different directions. So it's not just kind of like you have one force, one person pushing a box forward. It might be one person pushing a box, but then gravity is also acting and another person is also pushing it in a different direction, that kind of thing. So what we do in Specialist is we actually need to find the net force of the object. Alright? So, thinking about it like this, if you have two people pushing a box, alright, one is pushing it in one direction, the other one is pushing it in the other direction, we need to find out what direction will the box actually move in. What will the net force be? And by net, we kind of mean like total, like the sum of all of the parts, alright? If one person is pushing the box here, one person is pushing the box here, the box will move in the direction that the person pushing the hardest will want it to move in. Alright? So we need to find the net force. Alright? So, the resultant force, F net, is the sum of all of the forces. Alright? So you need to add up all of the different forces, including their magnitude and also including the direction of all of those forces. And as a result of that, this is equal to MA, because remember F net is equal to MA. You find the net force and you have the mass of the object, you can find how it will accelerate. So as a result of that, to find the acceleration, we need to find the net force first. Alrighty, so let's get into action and reaction. So an action is essentially the force of one particle or another, or more simplistically, an applied force is usually when you'll see it. So pushing a door open, pulling a box, pushing something over, throwing something, that kind of thing. It's kind of something that somebody does. A reaction is a consequence of Newton's third law. So what we're talking about in this sense is what's the result of that action, alright? So the second particle exerts an equal and opposite force on the first. So if we think about pushing a box towards a wall, right? If you push a box at a wall, that pushing motion will be the action, and then the reaction of that will be partly that the box will bounce back towards you. Alright? So a few common reaction forces you might encounter is tension. Now, I want to make one thing clear, just to jot down in your notes, is that whenever you're dealing with tension in a question, this can kind of confuse a lot of students because it's kind of like a different word that you're not necessarily used to seeing. But when a question talks about tension, all tension is just the force applied through any like string, chain, rope, anything like that. So if a question tells you there is so much tension, 5 newtons of tension, it just means that there's 5 newtons of force, alright? There's nothing special, there's no special equation to convert tension to anything else. Tension is just saying that the force is applied through that kind of like string or rope or chain, alright? But there's no special formula or anything you need to know there. Next, the normal force. So the normal force opposes gravity that an object exerts on another, alright? So a really common example of this is if you have a box sitting on a table, alright, gravity is pulling the box down, but the normal force exerted by the table pushes the box up, alright, and we could even think about this in terms of an action and reaction, alright. The table is reacting to the box being there by exerting an equal and opposite force, so that's why the normal force always acts perpendicular to the surface, or like at right angles to the surface, because the gravity is acting opposite there. Okay, so just because the forces acting on objects are both the same, it doesn't mean the result on each object is the same. So it actually depends on the size of the objects. So think about an example of a sumo wrestler who weighs 200 kilos running into a gymnast who weighs 40 kilos. So, just visualizing that in your head, if you have a sumo wrestler and a gymnast running into each other, you can kind of predict that the gymnast is going to bounce off, but the wrestler isn't going to move that much, right? And that kind of intuition matches up with what we'll see doing some calculations. So, let's find the force exerted by the gymnast on the sumo and the resulting acceleration experienced by both people. Alright? So, as we can see, the force is always equal to the mass multiplied by the acceleration. Alright? So, we know that the sumo exerts a force of 800 newtons on the gymnast. Alright? So the force exerted by the gymnast on the sumo is also going to be 800 newtons. And that's because, remember, going back to Newton's laws, every action has an equal and opposite reaction. So what that means is that the force in the opposite direction, or the reaction force, will have the same magnitude. So it will also be 800 newtons. Alright? And by opposite, we just mean that it's in different opposite directions. Alright? So this will be 800 newtons. The resulting acceleration experienced by both people. If we know that 800 newtons of force is applied, the acceleration now just depends on the mass of both of the people. So for the sumo wrestler, the mass is 200. Alright? So our acceleration is going to be 800 divided by 200, which is 4 meters per second squared. However, for the gymnast, we're going to have that 800 is equal to 40 times acceleration. Alright, so the acceleration is going to be 20 meters per second squared, because we're going to have 800 divided by 40. Alright, so as you can see, the sumo is going to travel a lot faster. Sorry, the sumo is going to travel a lot slower than the gymnast. And that is because the the gymnast is so much lighter that even though the 800 newtons was exerted on both of those parties, that force affects the gymnast to a much greater extent because it requires less energy to move the gymnast. All right, thinking about this really granularly, the force that you have to exert to kind of push over a bookshelf is a lot more than the force you have to exert to push over just a single book. All right, and that's because more mass, it requires more energy to move. So even though both the gymnast and the sumo wrestler experience the same amount of force, the sumo wrestler will not move as fast because it requires more energy to move him. Alright, let's move on. Now we're getting on to concurrent forces. So concurrent forces is what we need to focus on when there's multiple forces acting on an object. And what always helps is to draw a diagram. And this is almost always necessary unless you have a very, very simple question. It's almost always necessary to draw a diagram. Alright? So, especially when you have forces acting in different directions with different angles and that kind of thing. So, here we have two people pulling on a rock. Both people exert a force of 1,000 newtons, but person A pulls to the right and person B pulls upwards. What is the net force on the rock? Yep. So, let's draw a diagram of this. So we have our rock. Alright. Person A pulls to the right. Person B pulls upwards. Alright. So this is A, this is B. They're both exerting a force of 1,000 newtons. So we're going to label those sides. Remember, this is a force diagram, so the length of those sides there is equivalent to 1,000 newtons. And we're going to draw our vectors in the direction that the rock is being pulled in. So that's why we have those arrows there. Alright, so there's a few different ways that you can solve this, and personally I like a more geometric approach just because I feel like it is way simpler. But if you'd like, you can also use the approach of resolving forces into horizontal and vertical planes, I and J planes. So, let's go through my preferred method first. So looking at this diagram here, hopefully you guys remember the principles of adding and subtracting vectors. So remember, if you have two vectors, to add or subtract them, all you need to do is you need to move them head to tail. Alright, so the vectors that we have here are tail to tail. So the tail of the vector is the end of it, and the head is where the arrowhead is. Alright, so here our two vectors are, I'll write at a right angle there. Our two vectors are tail to tail. So what we need to do is we actually need to redraw this where the vectors are head to tail. So all you need to do is just kind of like slide your vector along. So all I did here is I just slid that A vector along because we still have the same relationship happening. It's just that our vectors are now added head to tail. Now what we can do here is draw the resulting vector. So to draw the resulting vector, you just need to draw almost to kind of like complete the triangle. So this is our F net. Alright? So now we can actually add these two vectors together just by figuring out the length of that F net line there. So how can we figure out the length of that F net line there? My preferred method is to just go through all of the rules that you know and equations that you know, and just treat it like, a regular triangle or a regular, whatever kind of shape you're working with. So here we just have a right angle triangle, meaning what formula can we use to find that length there? Pythagoras. we're going to have f squared equals 1,000 squared plus 1,000 squared. So let's see what this gets us. F equals 1414 newtons. Right, now, going back to the tips that I was giving you guys before to do with vectors is remember you always need to find the direction. Even though the question didn't explicitly ask for the direction, you always need to find it. Alright? It asked us for the net force. Force is a vector quantity. We need to find the direction. So, to find the direction, using this method, all you need to do is you need to just kind of figure out what angle the resultant vector, which is f net here, is from the horizontal. So we just need to find this angle in here, theta. So as you can see, the maths of it really isn't too difficult. It's just applying things you probably learned in year 10, year 11, like methods. It's more so just the new context. It's a little bit confusing. So, when you find this angle in here, you can determine, how upright the resulting vector is or how low. Alright? So, if a lot more force was being used to pull upwards, instead of both our forces being equal, if a lot more force was used to pull upwards, then you'd expect that the angle would be a lot greater, because that would mean that the rock has more force acting upwards, alright? But here, because both of our lengths are the same, we actually have an isosceles triangle, which means that this angle will be 45 degrees. Now, usually, you would just need to use sine, cos of tan to figure that out, but we don't even need to do that here because we already know that this is an isosceles triangle, so we know that it has to be 45 degrees there. This is the kind of question you would expect to get in a calculator-free test because you don't actually have to do any calculations to figure that angle out. And you don't have to use like too many exact values, which I think they do use in specialists, but they tend to stray away from a little bit just because it is more methods content. So they definitely do use them for sure a lot, but I mean I don't think they tend to rely on them too much. So just kind of looking out for that kind of thing really will help you out in that area. So this gives us our net force. So we have a force of 1,414 newtons acting at 45 degrees to the horizontal. Alright? Now, the next method that you can use of solving this, and sometimes this method is easier, it just depends on the question, how complex it is, this kind of thing, is instead of drawing this out like graphically, what you can also do is resolve the forces into horizontal and vertical planes. So, what you can do here is resolve the forces into I and J components. Alright, so looking at the diagram we have here, we have 1,000 newtons to the right and 1,000 newtons upwards. Right? So the actual maths that we will be doing here isn't really that different, but if you get into a more complex question, then the two methods are a little bit more different. Alright, so force A, person A, is 1,000 I, and force B is 1,000 J. Now, the resultant force will be the sum of these. Alright? So we're going to have 1,000 I and 1,000 J. Now if you'd like, you can pause the recording here and see how we're actually going to get the answer to the question here. Have a think about it. If we just think about drawing this graphically with our J and our I planes, our vector right now is like here, all right, at 1,000, 1,000. So when we're finding the net force, we need to find the magnitude of this vector. How do you find the magnitude of a vector? Remember, we're using our straight brackets to represent magnitude. How do you find the magnitude? The square root of both those components squared. Sorry, that looks like 600, but it's 1,000. And this is exactly the same maths that we did here. All right? And this gives us, again, 14 newtons. So we're getting the same answer, it's just a little bit of a different, it's not even the maths isn't too different, it's mostly just that the actual context is different. As I said, when you get into more complex questions, the maths might actually look a little bit different depending on how you figure it out. Anyway, then to find the angle here, again we need to find this angle there. You could again use that rule of considering that it's an isosceles triangle. When you're looking at like the vector plane, I guess it's kind of less obvious to think of that instead of looking just like directly at a triangle. So what you would do here is how you would usually just figure out the angle of a vector, just use tan. So we know that tan theta, alright, is going to be the y component over the j component. So the y component over the x component. And this again would give us 45 degrees. Alright, so same answer, just different method. It really just depends on what you prefer. As I said before, I prefer this first method just because it seems easier to me to just use and a little bit less finicky. But if you do prefer this vector INJ method, then that is completely fine too. And as I said, sometimes you will actually need to use one or the other. So it does pay off to kind of understand both of them. Alright, getting onto this question here, this one is more complex. So what I recommend is for you guys to pause the recording, have a go at this yourself, see how you go, and then watch the solution as we go over the answer. So, consider this picture hanging on the wall. A and B are the forces of tension of the two cables hanging the picture up. These forces are both 50 newtons, and the angle each cable makes with the horizontal is 30 degrees. How heavy is the sign? Now this is one of those questions where if you're not familiar with the content, it's one of those questions where it feels like they give you a lot of information and then they ask you a completely unrelated question. You know, like the I component is 3, the J component is 4, like what's the radius of the sun kind of question. So don't stress if you're reading this and you're like, what does this even mean? Alright? So, the first tip that I have for you guys, as I was saying at the beginning of the lecture, always look out for the F equals MA. Because a lot of the time, if you look at a question and you really don't know what to do with it, some of the time, or most of the time, it's because you've forgotten F equals MA. Alright? And as soon as they ever mention anything about weight or mass, alright, you think F equals MA. Okay? So that's my immediate thought there. Now this might not actually be what we end up using in the question, but just to be something to look out for. Alright? So, next let's draw a diagram. So, we'll actually just go over to the other page and draw the diagram. So we have the two forces hanging the picture up and they're both 50 newtons. So, we have them both like this, and both of the forces are acting like this because they're holding the painting up. 50 newtons, 50 newtons. We also know that each cable makes an angle of 30 degrees to the horizontal. So, really think about where you're going to put this angle before you put it anywhere. Because a lot of people would kind of see that angle and immediately put it in here. that is not correct. So when we're talking about angles to the horizontal, it actually means draw a horizontal line, and the angle between your vector and the horizontal is that. So that is where our angles are. Right? So we need to figure out how heavy is the sign. Alright? So when it's asking us how heavy the sign is, it's not actually asking for the mass. So there is a bit of a distinction. Remember, there is a difference between weight and mass, which I know, like just in everyday language, they mean just absolutely exactly the same thing. But when we're looking at maths and physics, weight and mass are different. Mass is like how much matter there is, so that would be in kilograms. Sorry. Yeah. And then weight. No, am I mixing those up? I'm so sorry. I'm actually just having a brain blank. Mass is how much matter there is. So that will be in kilograms, and then the weight is how much force is, how much force that object is being pulled down by gravity with. Alright, so weight will be in newtons. Alright, it's a force more so. Sorry about that. Alright, so let's continue on. We know that we need to find mass and weight, or in other words, we need to figure out what is this downwards vector, almost. Alright? What is that downwards vector? So, let's have a think about just what's happening with this sign. We have the sign hanging up. It's not moving. So this tells us that the forces are balanced, right? We know these two chords are holding the picture up. So what that tells us is that the force holding the picture up is equal to the force pulling it down. Alright? Because nothing is moving. If our picture was like slowly falling down, that might mean that the force down is greater than the force up, but that's not happening here. So we know these two are equal. Alright? And the reason that this is important is because when we're looking at F equals ma, which we know does have some relevance because we're talking about the heaviness of the picture, we have acceleration in there. And we also have force because that is related here. Alright? So we know the acceleration acting downwards is going to be negative 9.8 meters per second squared. Alright? So, let's find the resultant force. Now, we know that our vectors here are not added head to tail. So we need to do that before we can do anything graphically. Now, again, you could follow the other method where you find the I and J components. So you can feel free to do that one as well, and we'll go over that in a second. But just sliding that vector downwards, as you can see, our vectors are now added head to tail. The complicated thing now is actually just remembering those angles. So we know that we both have 50 newtons here, 50 newtons here, and we know that this is our resultant vector, but we still have those angles. So the angle that was already present is this one, which is 30. And we also slid that other angle down, which is 30 here. Degrees, sorry. So, hopefully you guys remember the Z rule. Alright, so this will tell us that this angle here is also 30 degrees because remember those two horizontal dotted lines are parallel, so you can use the Z rule there. Alright, so this tells us that the triangle we're trying to find looks like this. We have two 30s there, which means we have 60 degrees, 50, 50, and this is our force vector that we would like to find. So, we can use our cosine rule here to find that. So we know that f squared is going to be equal to 2 times 50 squared minus 2 times 50 squared cos 60. Let's see what we get here. We get an answer of 50 newtons. Alright. So, you could have even figured that out, considering that this is an isosceles triangle. We know that the two angles in here have to be equal. Alright, considering that one of these is 60, the only angles that these could be is 60 as well, meaning that it's actually also an equilateral triangle. Alright. Okay, moving on. So, we know that the force acting to hold that picture up is 50. So, the force up is 50. Now we know that the force down is equal to the force up. We have a net force of 0 because nothing is happening. Nothing is moving, so we have a net force of 0, acceleration 0. Alright, so we know that 50 is equal to ma. We know that the acceleration acting downwards is 9.8. So this tells us, acceleration due to gravity is 9.8. This tells us that the mass of the picture is 5.1 kilograms. If it asked you for the weight, it's kind of unclear with use of heavy. If it asked you for the weight of the picture would be 50 newtons, but the mass is 5.1 kilograms. Alright? Okay, so again, going back to your strategy, looking at this question, knowing what to do. As always, notice anywhere where they talk about weight, mass, anything like that, think about F equals ma and how that can come into play. Always draw a diagram. And then I guess something else that you should be looking out for is the force due to gravity. If gravity is a force that you feel like is acting on the object, like in this scenario here where gravity is pulling the object down, make sure you're considering that the acceleration due to gravity is 9.8, alright? And that will always come in helpful too. So don't stress if you looked at this question, you didn't even know what to do, it's okay. It comes with practice, you have plenty of time before your externals. Once you've gone through a few of these questions and you kind of get into the rhythm of it, you tend to pick up on the patterns and see when they're asking for you to use F equals ma, when are they asking for you to use 9.8, when are they asking you to resolve these particular vectors, any of that kind of stuff. Right? Okay. Now let's get on to an even harder example. So, the hard example here is looking at inclined planes. Alrighty? Now there is a little bit on inclined planes getting into external, and if you have a look through the mocks and the previous externals, you will see a few of them. So when there are multiple forces acting on an object, things can get a little bit confusing. So in these scenarios here, it really is just a little bit about practice and a few formulas and things you need to remember. So we have a mass of 200 kilograms here, that's what it tells us. We need to find F in terms of mu, so that the object can stay at rest on the ramp, or move up at a constant velocity. So, we need to find F in terms of mu, so all that's asking us is find an equation where you have F on one side, and on the other side you have a few constant numbers like 1, 2, 3 kind of thing, and mu. Alright, we don't have any other like unknowns or variables. And we need to find it such that the object is at rest. So when an object is at rest, it means its velocity is 0, right, because it's not moving. Or move up at a constant velocity. So let's have a think about this. What would it mean if an object was moving up at a constant velocity? It would mean, firstly, that the acceleration is still 0, as it was here. Alright, because it's a constant velocity. If the velocity isn't changing, it means the acceleration is 0, right? Because the acceleration is the rate of change of the velocity. And if it's moving up the ramp as opposed to down the ramp, it would mean that the force up the ramp, force up, is greater than mu. Alright, so those are the two scenarios that we have there. But I think the common one, which the question is really asking us to look at, is the fact that the acceleration is equal to 0. Alright, we also know that the angle of the incline is 30 degrees. What we can also do is point out what a few of these forces on this inclined plane mean. So, the F acting up the plane is actually just the applied force. So if you think about having a ball on a plane, maybe you have a string attached to the ball or something and you're pulling it upwards, parallel to the plane, that's the applied force. This one here is the force acting down the plane. Alright? So, this usually is a result of gravity, because gravity is obviously pulling the object down the plane. It's not directly proportional to gravity, but it is related to gravity. Just one other thing I will mention is sometimes you'll also get talked to about friction. So friction can also can also be a force acting up the plane. Alright, because if there's friction, it's restricting the ball from rolling down. Or if the ball is actually rolling up, then the friction will be acting downwards. Alright, so looking at this example here and considering that this arrow is a lot shorter than this arrow, it means that this force is bigger than this one. Alright, because it's longer. So, what's actually happening is the force pulling the ball up the plane, alright, is being opposed by the gravity force down the plane and also the friction force. So friction always acts opposite to the direction of motion. Alright? I mean, think about just having a box on a piece of carpet. If you push it away from yourself, friction will oppose you. If you pull it towards yourself, friction will also oppose you. Alright, friction is just kind of always opposing whatever you're doing, essentially. Friction is always opposing you. Friction is the enemy. So when you're thinking about friction, it always opposes the direction of motion. Okay? This force acting here is the normal force, and as you might notice, this normal force is actually perpendicular to the inclined plane. It's not perpendicular to the ground. It's not acting straight upwards. It's perpendicular to the plane. And you can also calculate the normal force using an equation that we'll get into later. This force acting downwards is the force due to gravity, mg. So remember, F equals ma. Here, force due to gravity, Alright, G is actually the acceleration because G is the acceleration due to gravity, so that's why we write it like that there. And that, of course, is acting directly downwards because that's how gravity works, right? Pretty intuitive. So, before we move on and actually complete this question, let's have a look at the easiest way to actually do it. Alright? Instead of drawing it like this, like directly onto this inclined plane, if you just rotate this, it will be a lot easier. Alright? Because now only one of our lines is not on an axis. Alright? Which makes things a lot easier. So, let's continue on and solve this question. So what I'd like you guys to do is pause the recording, have a go at it yourself first, even if you're not super confident, just have a little bit of a go at it, and then you can watch me go through the solution. So, we need to find the force such that the object can stay at rest. So we know we know what the force down the plane will be equal to, and this is a formula that you need to remember. So the force, I'll just call it force down the plane, is equal to mg sine theta, where m is the mass of the object, g is 9.8, acceleration due to gravity, and theta is the angle of incline. So, mu, force down, is going to be equal to mass, which is 200 here, times 9.8 Alright, sine 30. Alright. However, if we have a look at our diagram here, alright, it actually is a little bit easier if instead of using that 30 degrees, we use the 60 degrees here. Okay? So what we can actually do here is we can figure out the horizontal and vertical components of this vector. This one here. Alright? So, we know that the length of the vector is mg. We know that the angle is 60 degrees. So the x component, right, will be mg cos 60, and the y component will be mg sine 60. Now, we know that the mass is 200 and g is 9.8, so we can figure this out fairly easily. Alright, mass 200 multiplied by 9.8 multiplied by cos 60 gets us 980. And then same thing here, 200 multiplied by 9.8 sine 60, which gets us 1697 newtons. That's I, and this is J. Alright, so that is how we get our vertical and horizontal components. Now what we need to do here is find the overall net force. So our net force, alright, is going to be, and we'll start with the I component, we need to consider which forces are acting in the I component and in the j component. Alright? So, in the I component, we have mu n and f. Mu n and f. Alright? So, we have the component 980 and the f and the mu n. Alright? So, the biggest force is the f, meaning when we're looking at our net force, we're going to have f minus the mu n force minus the 980 force. Alright, because looking at it, we have the horizontal component of this force we also have around here, but both of these are going to be smaller than this big one. Alright, now getting onto the j components, we're going to have the normal force, because remember, in the j direction, we have the normal force, and we also have the vertical component of this vector here. So we're going to have the normal force minus away this 1697 here. Right. Now, remember what we were talking about before, for the object to be at rest or moving at a constant velocity, the acceleration equals 0, and thus the net force equals 0. So that's what we were talking about when we first looked at the question, alright? So we know that the net force has to be 0. All we need to do from here then is to let both of these I and j components equal 0. And we can do these separately, remember? You can always separate those I and j components, which usually makes things quite a bit simpler. And the reason that is because it means if you have a particular variable in one of those I or j components, you can separate it out. You can do the same thing with imaginary and real components in complex numbers, and that also helps quite a lot. If you know the real component is equal to a certain thing, and the imaginary component is equal to a certain thing, that can really help. So, as you can see, I just rearranged to isolate f there. Now I'm going to let 0 equal that 1697, that j component. As you can see, we can see that n is equal to 1697. Alright, so this means that f, putting this in, is going to be 1697 mu plus 980. And this is the answer that we were asked to find. We were asked to find f in terms of mu. Alright, so all we needed to do for this question is we needed to resolve our vectors into horizontal and vertical components, and then just find the sum in the horizontal and vertical directions. Alright, and as you can see, rotating our axis really helps with that. Alright, so just some tips with modelling motion. Always draw diagrams and label all forces with directions and angles. If you have a flat surface, there's no orientation change that you need to make. But if you're on a ramp, it usually helps to set out I and j so that they're on the same plane as the ramp. You can rotate those axes. It makes things a lot easier. The question we just went over probably isn't the only type of vector resolution you'll get, but it does cover all of the fundamental principles. And looking at the questions that we've looked at so far, they do definitely cover all of the fundamental principles. So if you're worried about the modelling motion questions getting into your external, we have covered the basic principles. What I would recommend is going over the previous external questions and seeing what you can find in there. I do remember there are a few questions on inclined planes, but I can't remember any of them being too complicated. Certainly a lot easier than the one we've just done. Some of the other modelling motion questions involving vector resolution aren't too difficult either. In my opinion, the more difficult modelling motion questions actually involve the questions we're going to get into next. So if you're already familiar, the questions involving all of those equations for acceleration that are written on your formula sheet, those in my opinion are the more complex ones, and they do turn up on your externals. So we'll get onto those next. Now we're getting onto, and you'll see what I'm talking about, these equations here on your formula sheet. A lot of students that I've had tend to struggle with these, and when I was learning them, I tended to struggle with them too. It's almost just a matter of like too many equations, too many variables. It's just you really need to practice and like get good at them. And even then, it still can be quite confusing. So, we're not just going to look at these equations, we're also going to be looking at simple harmonic motion, which you might be familiar with. Those are the questions involving moving around in a circle or a spring moving, sine curves, that kind of thing. So let's get onto these now. We don't actually need to go over these too much, but just for your information, these are the equations that I am talking about here. Alright, we have acceleration is equal to dv dt, firstly, and this should be familiar to you, right? Acceleration is the rate of change of velocity with respect to time. The next one is acceleration is d squared x on dt squared, and this should also be familiar to you because x is displacement, so all we're saying is acceleration is a second derivative of displacement, which you should also be familiar with, right? These next ones are where it gets a little bit complicated. So acceleration is velocity multiplied by the derivative of velocity with respect to x. So where these tend to get a tiny bit complicated is where you kind of forget that it's with respect to x and not t. Okay, and that's really the most common mistake that most students make, is kind of mixing up which variables are in there. So if there's any tip that you take away from this lecture with respect to this topic, is to just make sure you're looking at these equations, and making sure you're using the right variables, especially with the x's and t's, because you're so used to, when you're doing acceleration, you're so used to doing things with respect to time that doing it with respect to displacement seems wrong. But I guess you just need to be aware of that and make sure that you're not making those mistakes. The next one is the derivative of half v squared with respect to x is also equal to acceleration. So this one is a little bit complicated too. So, as a few tips, if you're given acceleration in terms of x, you can use this formula, or this one we're looking at here, to get v squared in terms of x. Alright? Because if you're given given in terms of x, right, you're saying a is equal to x squared or something, you can put this on one side. Alright? So say you have a is equal to x squared. This is what you're given in the question. If you use this formula, you can go, well, a x squared is on the left-hand side is equal to d half v squared on dx, and then you can use some differential equations. So you can take this up and say that that's x squared dx and solve it from there. Alright? Then if you're given a in terms of v, you can use a equals v dv dx, and then do a similar thing with differential equations to get x as a function of v. Alright? And then solve using differential equations. So, let's go through this question here. So we have, and this is quite a complex one, so if you're more of an advanced student, please feel free to pause the recording and have a go at this yourself, or if you just want to come along for the ride, then that is absolutely fine too. So we have a particle being projected upwards with an initial velocity u. The air resistance on the particle is 7 mv squared, so air resistance 7 Find the maximum height the particle reaches in terms of u. Max height in terms of u. Right. So, let's go through this, alright? We have a particle being projected upwards. It's being projected upwards. That tells us that all of the force being put in is just acting upwards. We don't have any complicated angles to deal with or anything. Or in other words, the angle of projection is 90 degrees. So that makes things super easy. So we know that the air resistance on the particle is 7 mv squared, and we also know that the maximum height occurs when the velocity is equal to 0. How do we know this? Alright, we know this because if you're thinking about a particle being projected upwards, the time when it reaches its maximum height is like when it gets right to the top. And if you think about like throwing a ball upwards, when it gets right to the top, it kind of stops for a second and then comes back down again. So something that you need to remember for these like projectile motion questions is the maximum height occurs, and it occurs when the velocity in the j direction is equal to 0, more specifically. A lot of the times you'll get questions where it's not just projected upwards, it's projected like to the side as well. I know I believe it's the 2020 paper 2, there's a question involving projectile motion and a cart, which would be useful to go through if you want some more practice, or maybe it's on the mock. I think it's in the 2020 paper 2, or maybe it's paper 1. It's the last question, and it just goes over projectile motion and a cart in a wall, which is a really good practice one too. But when the velocity in the j direction or the y direction is equal to 0, then you have the maximum height. Because our ball is projected, or our particle, sorry, is projected straight upwards here, we don't need to consider that, alright? Because all of the velocity is already in the y direction, because it's already just going straight upwards, alright? So, let's consider now what the net force is. Alright, so the net force on the particle, alright, let's have a think about what it is. If we have the particle being thrown upwards, alright, and then we think about the force also acting on that particle as well, we know that the net force is going to be mg, because that's the force due to gravity, remember, minus the 7 mv squared that we were given as air resistance. Alright? Because we have the ball being thrown upwards, and the only force which is resisting that is the air resistance. Alright? Okay. So, let's continue on. We want the height reached, which means we need the x value. Alright? Okay, so sorry, I just made one small error there. So since the ball is being projected upwards, the force due to gravity and the air resistance both act against it. Alright, that's what I was getting confused about there. So, continuing on from here, we now know the net force. Alright, the next thing we can figure out is we can figure out the acceleration, because we know that the acceleration be negative g take 7v squared. How do we know that? Think about it like this. F equals ma. Acceleration equals force divided by mass. Alright, so if we divide this by m, we will get this acceleration formula here. Alright, let's move on. So since we want to get the height, we need to get x in there somewhere because x is the position of the ball. Alright, we want to get the maximum height, which will be x. So, what we have over here is a as a function of v. We have a as a function of v. So we need to think about what equation we can use to actually get x in there. We have a in terms of v. I want you guys to have a look back to your formula sheet. See what formulas are on there and have a guess as to what equation we can actually use here. Alright, so you have a in terms of v and we want to get x in there. If you guessed a equals v dv dx, you'd be right. Alright, because this one includes a and v, which is what our a equation is in terms of, and it also includes x. Remember, x is the height, because that's the x is the displacement. Our particle is only being projected upwards, so the displacement is only in terms of y anyway, so the x is the height. So we want the height in there somewhere, because that's what we've been asked. So this is the perfect formula to use. Alright, our acceleration is negative g take 7v squared. Alright, plus, sorry. And this is going to be equal to v dv dx. Alrighty. Now, we want this x right here. We want x equals, because that will give us the height equals. That's exactly what we want. So we want to somehow extract that x out of things. How can we extract that x out of things? Alright? Well, we have a differential equation there. So the first thing we're going to need to do is solve that differential equation. To do that, we need to get rid of this v, take it over to the other side. So we're going to have dv dx equals negative g plus 7v squared on v. Now we can solve this differential equation. We want to get x equals, so we want dx on the top. Alright? We want to isolate x, which means we want to have dx on the top. So we're actually going to invert this whole fraction. Alright? Now that we've done this, we can solve this differential equation. Take this dv over. Alright? So, we now have that x is equal to the integral of negative v on g plus 7v squared dv. Now, to solve this, I want you guys to have a think back to those integration methods that you would have learned towards the beginning of the year. Alright? And remember, you always should be looking out for components of an equation that you're integrating, that include the derivative. Alright? So where one part of the function, the derivative of that would cancel out the other part of the function. So here, if we do a little bit of nonlinear substitution, so we have w, whatever function we'd like, is equal to g plus 7v squared. We find the derivative, we would have 14v, right? get dv by itself. Substitute this back in. X is equal to the integral of negative v over w multiplied by dw on 14v. As you can see, those two v's cancel out, right? So that was just a really quick application of that nonlinear substitution. If you were a little bit confused by that, make sure you hop back to those initial few chapters that we looked at integration methods. Because I don't have too much time to explain it now. Alright, so we have here, we can obviously have negative 1 on 14 multiplied by 1 on w dw. So obviously we can just integrate this as just an ln function. So we're going to have negative 1 on 14 ln, and then w is going to be just that original substitution we did. Let's see. Alright, now our initial condition here to find C is actually quite simple, because we know that the particle, when it was initially thrown, was at rest. Alright? So, we know that when x equals 0, our velocity, we know that when time equals 0, x of 0 is equal to u. Alrighty. So, let's just continue on from here, and I'll actually have to erase a little bit of this because we only have one slide, fortunately. So, given that initial condition, we know that C is therefore going to be equal to 1/4 ln g plus 7 u squared. Alright, and now just to add that C value to our original function for x, we're going to get that x is equal to negative 1 on 14 ln g plus 7v squared plus 1 on 14 ln g plus 7u squared. And now we can just use log laws to combine those two logs there, because they both have the 1 over 14 at the front. That first one is a negative, so that means we'll be using the log law where we are dividing. So we're going to have g plus 7u squared on top, and then g plus 7v squared on the bottom. Alright, the final thing we need to do is just remember that what we were going through before, at the maximum height, the velocity is equal to 0. Alright. So all we need to do is just sub v equals 0 in. So we're going to have x equals 1 on 14 ln g plus 7u squared over g plus 7, g. Alright? And that will be our answer there. Alright, so this question we just went through was quite tricky. So don't feel bad if you were a little bit stumped at first. It was quite tricky. If you got this in an exam, it would definitely be worth like 6 to 7 marks for sure. The main trick though, I guess, was just to kind of work through it systematically and not be overwhelmed by complexity of it, if you just go step by step, each step individually is quite simple. It's just when you look at the whole of it that it is really quite complex, alright? So try not to get overwhelmed by the full complexity of the question. Try to just work at it step by step, alright? Okay. Now let's get into simple harmonic motion. So, simple harmonic motion is the motion of an object back and forth about a central point, such as a pendulum. Alright? So, an object is said to be moving in simple harmonic motion if the acceleration is equal to negative omega squared x. Alright? So therefore, the acceleration is always proportional to the displacement, but opposite in a direction. As a result, the further away that the object is from the center, the greater the tendency is for the object to return to the center. So a really perfect example of simple harmonic motion I can think of is a spring moving back and forth. Alright, so I have a spring attached to a wall and it's kind of bouncing back and forth. Don't think about it being like pulled down due to gravity. Say we are in a vacuum. We're in a vacuum with a zero gravity location. With a spring. Alright. Because thinking about it, the spring has like a natural position that it's at, where it's like not really extended or anything. It's just resting there. If you pull it out, the closer it gets to the edge, the more it will want to, or the more extended it gets, the more it will want to like return to the center. If you compress it, it'll want to get back to the center again. Alright? But it's harmonic motion. Alright? There's a few different things that you need to understand about this, about simple harmonic motion. A few different qualities I think that you need to remember. Alright? But before we get into those, we'll actually just go over the notation. So, simple harmonic motion does have endpoints. So if you think about a spring, the endpoint would be like when it's most extended and when it's completely compressed. And we call those the amplitudes. So simple harmonic motion is actually very linked to trig equations, which is why a lot of the equations on your formula sheet related to simple harmonic motion are trig ones, if you're familiar with them. And that's why we have this amplitude stuff, because it's similar to the trig language. But essentially, if we just think about our spring, if on either end we have the endpoints of motion, alright, that's A, that's negative A, and this in the center is just 0. So essentially, A, the amplitude, is just the distance from the center to the endpoint, and that's very similar to how it is. It's exactly the same to how it is with trig equations, right? So, we actually won't solve the differential equations right now, just because it's a little bit too complicated. But I will show you guys what formulas we are working with. So, this one here is very important. Velocity squared is equal to omega squared multiplied by amplitude squared, take displacement squared. So, the omega, this is a capital omega, is the angular velocity. So, it's kind of like how fast, or rather, like how many degrees the object covers in a certain period of time, almost, right? Then getting into these next formulas, these ones describe the displacement, alright? So again, we have the angular velocity, and then we also have the phase shift. So, as per usual with any sort of trig functions, usually try to use either sine or cos so you don't have a phase shift, just because obviously it makes it more complicated, and we know that sine and cos are only a phase shift apart. And the same goes here. Try to pick either sine or cos, depending on which one will not have you use a phase shift, because it just makes things 100 times harder. Sometimes you will have to have one though, which is inconvenient. But again, just like with regular trig equations, all you need to do to find the phase shift is just find all the other values in the equation. So you'll have like the amplitude, the angular velocity, and then you'll have like a coordinate that gives you the displacement and the time. Sub all those in and then just solve for the phase shift. And that's all you have to do. Is just, it can take a little bit of extra time. It's a little bit inconvenient. Alright. The other thing you need to understand is that the period is equal to 2 pi over the angular velocity. So I believe this one is in your formula sheet, so you don't need to remember it. And then another thing is that the frequency is the reciprocal of the period. So the period is how long it takes for one cycle to be completed, and the frequency is how many cycles are completed per second. Alright, so if you're given information, make sure you don't mix up the frequency and the period, because something they can do like fairly easily to mix you up is give you the frequency instead of the period, and then you just like immediately sub it into some other equation. No. Make sure that you know which one you've been given, either frequency or period. Okay. Going back to those few properties you need to know. And these ones are really important. They're not on your formula sheet. You need to make sure that you understand them, because if you get a simple harmonic motion question on any exam, you'll almost definitely need to know this. So, at the endpoints of the motion, velocity equals 0. You can think about it in the fact that at either ends, the object will slow down and like turn around almost, and at the exact instant where it's turning around, and it's not going forward anymore and it's not yet going backwards, at that exact instant, it has a velocity of 0. Alright? Acceleration is in the opposite direction to the displacement. At the center of motion, the acceleration is 0. So the acceleration is 0 in the center of motion. That's the lowest acceleration. Alright? The other thing you need to know is that the maximum speed, and then both the maximum and minimum velocity. So remember, speed is the scalar quantity, like the one without direction. Velocity is the vector quantity, the one with direction. So the maximum speed, the time when it's going the fastest, occurs at the center of motion. Alright, that makes sense, right? Because that's like when it's turned around and it's going really fast, and it's right before it starts to slow down again. Alright, and obviously whether the velocity is a minimum or a maximum depends on what direction the object is moving in. Alright, so if it's moving left to right, then it will likely have a maximum velocity because it's a positive velocity. If it's moving left to right, then it will likely have a minimum velocity because it's like moving in a negative direction. Alright? And then another thing is that the magnitude of the acceleration is maximized at the endpoints. And that makes sense as well, right? Because that's when the velocity is changing the most, because it's turning all the way around at those endpoints. Alright? So, these things, it's really important for you to remember, because a lot of questions on exams will ask you, when does the maximum acceleration occur? When does the minimum velocity occur? Yada, yada, yada. Alright? Okay. Let's just now get into some more tips before we get into an example. So, for which equation, whether sine or cos, to use. If you're not given an equation and you need to find one for displacement, you like either the sine or cos one. Just a few tips on like whether to pick sine or cos to use, because you can use either. As I said before, try to make the initial phase shift 0. So essentially, thinking about cos and sine curves, remember a cos curve without a phase shift starts like this. So, yeah, that's okay. And then a sine curve starts like this. So hopefully you remember that. Terrible drawings, I know. But the point is, the cos curve starts at the extreme of its motion. It starts like right at the top or right at down the bottom. Whereas the sine curve starts in the center. So, if you've been given a question and you're told like the initial position, if the initial position of the object is at the extreme of its motion, if it's at A or negative A, use cos. If the initial position is at the center point or at x equals 0, use sine. Alright? And then obviously you can put a negative or a positive in front of those sine and cos depending on the initial velocity. Alright, which direction it's moving in. Alright, let's go through a question here. So, we're told that a particle is oscillating with acceleration equals negative 16x. Its speed at the origin is 24 centimeters per second. We need to find v squared, the amplitude and period, and the speed and acceleration. So, what I'd like for you guys to do is pause the recording, have a go at this yourself, even if you're not feeling too confident. Just have a go, and then see how you go when we go through the solution. So, we know that A equals negative 16x. Its speed at the origin, so at x equals 0, sorry. Its speed is 24 centimeters per second, not the velocity, alright? Its speed. So, usually when you're going through these questions, it's always easiest to start with the acceleration equation. And the only reason that is because it has the least number of variables. So the acceleration equation is acceleration equals negative omega squared x. Right? So, if we let our negative 16x equal our negative omega squared x, we can see a few helpful things. Our negatives cancel out, our x's cancel out, leaving us with angular velocity equals 4. Alrighty? And that is super helpful. So, the first part of the question asks us to find v squared. Let's go back to our formulas. We know that v squared is equal to angular velocity squared, a squared minus x squared. Right. So, we're going to have 16 for our angular velocity. Our amplitude, we don't know yet. Alright? So, we don't know our amplitude yet, but we'll be able to figure it out soon. And we don't know, well, x is a variable, so we don't need to put that in yet. We don't know our amplitude, so let's think of a few ways that we could figure it out. Alright? What other information do we know? Well, we know its speed at the origin is 24 centimeters per second. Alright? And we also know the angular velocity. So, we know that t equals 2 pi over omega, meaning that the period is 2 on 4 pi, right? Which is half pi. So we know the period, right? This almost answers this question. But how can we find the amplitude? Well, if you have a look at your formulas, you'll see that the only formula including amplitude in it are those two for displacement. Alright? So let's have a go with x equals a sine angular velocity plus angular velocity t plus the phase shift. We don't need the phase shift here, so we can just leave that out. So we know that its speed at the origin is equal to 24 centimeters per second. Alright. So we can either figure out the amplitude using this equation here, or we can actually just use this one here, because we know that at the origin at x equals 0, that's going to be equal to 24 minus 0. So we're going to get 24 squared divided by 16. So a squared equals 36, which tells us that a equals 6. Alright, so now we're up to part C. Find the speed and acceleration when x equals 2. So now we need to use this one here. Let's go over to the next slide. So we have x equals a sine omega t. Alright, so we know that a is 6. We know that angular velocity is t, as 4, sorry. We need to find the speed and acceleration when x equals 2. So we'll let x equal 2 and find the time at which x equals 2. And then from there, once we've found that time, we can put that into our formula, or actually no, sorry, we don't even need to. We can actually just put it straight in. Perfect. So we don't even have to do that. We can just use x equals 2 and put it into our formulas here. So we know that our acceleration is equal to negative omega squared x. Alright. So we know that our acceleration is going to be negative 4 squared multiplied by 2, right, which is negative 32. Now we need to find our velocity. So we have velocity squared equals 16, a squared, which is 6 squared, minus 2 squared, because that's our x value, so we're going to get v equals, so we're going to have 16 multiplied by 36, take 4, which is 32. This gives us an answer of velocity equals 22.63. So that should be in centimeters, sorry, because that's what it was given to us in, centimeters per second. Alrighty. Just a summary of our content on modelling motion. So, we went over how the net force is the sum of all the forces acting on an object, making sure you're always drawing out a force diagram, either solving vector problems by adding head to tail and doing some geometrical solving using like Pythag or sine and cos and tan ratios, or you can resolve the vectors into horizontal and vertical components, the I and J components, and then add those, making sure you rotate if you have a ramp. Using those equations for acceleration, making sure you're using the right variable in all of those, and how a lot of it is about just kind of looking at what you actually need to find, what variable that correlates to, and then figuring out what variables you have in your equation already and just kind of jumbling them up somehow, essentially. Moving on to simple harmonic motion. It's a lot about making sure you understand the formulas that you've been given for them. And then really a lot about practice. Remember those few properties that we were talking about when the maximum acceleration occurs, which is at the endpoints, when the maximum velocity occurs, which is in the center, when the velocity equals 0, that's at the endpoints, and when the acceleration equals 0, that's in the center. Alright? And then making sure when you're figuring out whether to use sine or cos, picking the one that you don't have to have a phase shift for. Alright. Let's get into sample means. So, we're not going to spend too much time on this just because I want to get onto the advice at the end. So we'll just do a brief overview. So let's go over sample means to begin with. So a sample is just a small part of a whole, subset of the population. Alright? So the height of 100 people in the population would be a sample of the whole population. If you have a sample, you can kind of make inferences about the population. Alright, if your average height from those 100 people is like 1.7 meters, you can kind of say, well, you know, the population average is probably going to be around that. And obviously we can make more complex statistical assumptions, but that's kind of what we're doing there. Alright, so we can actually make multiple samples, and this is where the content that we do in Specialist differs a little bit to that in methods. Because in methods, we're just more so looking at one sample. In Specialist, we actually look at taking multiple different samples. So, getting into the assumptions of taking samples, samples are independent from one another. In other words, you know, sample 1 has no effect on sample 2, doesn't matter. They're identically distributed. So if there's an underlying distribution behind each sample, such as a normal or a binomial, then they will all be the same. Alright? Okay. From methods, you can consider the binomial distribution about rolling 6s in 20 rolls of a dice. But if you were to do this 500 times instead of 20 times, the distribution that you see will approach a normal distribution. Alright? So, alternatively, instead of treating it as a binomial distribution, you can treat each set of 20 rolls as an individual experiment and run the experiment 500 times. If you do that, we have 500 samples, and each of those samples follow a binomial distribution. The sample mean is just the average of the values of each of the samples, and thus the sample mean, which we denote with x dash, can be given by all of the values of the samples added up divided by the number of the samples. So the mean and standard deviation, right? The mean or the population mean is given by mu, and the population standard deviation is given by sigma, but we actually have different symbols for sample means. So the sample mean is given as the expected value of the x hat, and then the sample standard deviation is given by a lowercase s. So just as a quick simulation, I actually think we might, I'll leave this for you guys to have a look at in the slides. It is interesting, just to understand a little bit of um, how experiments approach a normal distribution. So go over that, but we'll just carry on from here. What we do in Specialist is considering that the more samples that you take, the closer a distribution will be to a normal distribution. So as you can see here, with one sample, we don't really look like a normal distribution, but as we take more and more samples, the distribution approaches that of a normal distribution. So, in Specialist, we have something called the central limit theorem. The central limit theorem essentially just tells us when a distribution will look normal. Alright? So, regardless of what the population distribution initially looks like, as n becomes larger, it's a better approximation. Alright? And then the mean of the samples is going to be the same as the population mean, and the standard deviation of the samples will be the standard deviation divided by the square root of the number of samples taken. And here we can see a nice visualization, alright? Looking at the population distribution, alright? Taking 5 samples, as you can see, the distribution looks somewhat similar to the population distribution, but as you take more and more samples, they will all approach a normal distribution. The magic number is 30. Alright? So there has to be more than 30, more or equal to 30 samples for the distribution to look normal. And it is actually important to know this. I remember on my external there was a question about why a distribution could be approximated as normal. And the answer, it was only like 1 or 2 marks, but the answer was just that the sample size was greater than or equal to 30. Alright, with all of this out of the way, let's get on to some external exam prep advice. Alright? So I'll just go over this in the last 10 minutes or so. Just as I know you guys are coming up to externals, and probably one of the more important things that you're after is not just to go over the actual content, because you went to class for that and everything, it's actually just for a little bit of advice. So specifically for external exam prep, go through each dot point of the syllabus, write the general process for that question, and this is especially important for specialists because there's such a wide breadth of content. It can be kind of difficult to always know what you need to do. Alright? So go through each dot point and write the general process for each type of question. And like as well, I know in methods, a lot of the time you don't really need to write the general process because it's quite straightforward. But in specialists, there is usually a kind of a particular process that you need to take. Alright? And also any strategies that you pick up. So, once you get the basics, practice the hardest questions that you can find. And this is really important for specialists too, because they kind of tend to throw a few difficult questions at you. This really develops your problem solving skills and helps you understand the concepts far more thoroughly. So that's one of my biggest tips, is just to practice difficult questions. Alright? Now, the main benefit of this is actually you figuring them out yourself. It's not necessarily going to the answers. So, in terms of prioritizing, make sure you know how to do each of the simple familiar types of questions, because that will get you the bulk of the marks. Once you are actually all over the simple familiar questions, go back and do hard questions for each of the topics. As I was saying at the beginning of the lecture, don't neglect don't neglect any of the syllabus documents. Alright. Use as many resources as you have available. So different textbooks, study guides, libraries, even Googling questions is really helpful. You don't want to just kind of be prepared from one textbook that your school provides and then kind of miss out on anything. So if you're able, find some different textbooks. Usually a good place to get them is like secondhand bookshops, especially around the kinds of areas where, it depends where you live, but in the areas with more private schools where students maybe buy their books themselves as opposed to them being provided by the library, like in public schools, you might tend to find more secondhand textbooks. And of course, they don't need to be like super up to date because the syllabus hasn't been updated since 2020. So you don't need to worry about that. Alrighty. Here's just a snip of some of the notes that I was taking to cover all of the syllabus dot points. As you can see in the green bolded text, those are the syllabus dot points, word for word. And then underneath, I just have my notes. So it obviously depends on what type of content it is. If it's one of those things where there's a formula you need to remember that's not on your formula sheet, I've written that down. So for vectors and matrices, or for the equation of a sphere, midpoint, that kind of thing, equation of a straight line, all that kind of thing, I've written it down. Where there's not an equation you need to remember, but more so like there's a few different common strategies that you need to use. So for example, for proof by induction, I've written those out as well because most of the time all of the strategies you'll come across are on your external. You'll have in your notes there. If you do a wide enough variety of textbook questions, that is what you will get. Alright, here's just another example. If there's a particular topic that you maybe have a little bit of trouble with or anything like that, such as integration, I did have a whole document just on integration, all the different integration methods, that kind of thing. Just kind of writing a big document of all the different types, all the different strategies that you tend to see. So, as an example, simplifying things in this form, you can follow these steps to get to, if you have a sine or cos multiplied by x, then you can follow these steps to integrate it, that kind of thing. And it's really explicitly writing down everything that you see in your textbook. I do have some tips on internal exam prep, but you don't need to worry about that. General exam prep, make a list of the notes that you make, of the mistakes that you make, sorry, that's really helpful, especially if there's something that you like really commonly tend to do. Such as if you always forget the pi when you are finding the volume of solids of revolution, that's something that you can write. Make sure that your algebra skills are up to scratch, because a lot of students kind of like have a really good understanding of the concepts taught, but just kind of haven't really practiced enough complex calculator-free questions to really develop those algebra skills. And you might be surprised by actually like how much algebra you need to do on your external, on your calculator-free one, I mean. Feel free to read some books to help you with your motivation if you feel like it. During your exam, one of the biggest things is students being really high achievers and knowing a lot about the content and practice a lot, but they just make small mistakes that add up or just get stressed, right? So my tip for making small mistakes, because I've been there and I've done that, is to just be like ridiculously thorough. Alright, so whenever you're going through a question, copy this formula exactly from the formula sheet correctly? Did I write down all of my values correctly? I haven't misread a number because I wrote it messy. I typed everything into my calculator correctly. I didn't like forget brackets or anything. Mentally check your arithmetic. So mentally check whether you have done the correct arithmetic there. For managing stress, figure out some other strategies that help. So make sure that you are practicing a lot, because then when you get into the exam, even if you're really stressed and you feel like you're forgetting all of the content, if you've practiced a lot, then you will be far less likely to actually forget what to do, because it's just kind of like muscle memory at that point. Also, just kind of fix your negative self-talk a little bit. That sounds very cliche, but make sure you're just thinking positively about the exam, thinking positively about the revision. It really does make a difference, I promise, even though it sounds very cliche. For complex questions, make sure you're communicating everything. You don't want to lose communication marks, writing headings, writing all the formulas, defining all your variables, that kind of thing. Make sure that you're also looking at how many marks a question is worth. If you're looking at a question and you've kind of got a whole page of working and it's worth 3 marks, you know, you're kind of going down a rabbit hole a little bit, and it was probably a lot simpler. So make sure you are kind of looking for that kind of thing, and always thinking about, like, is the amount of work I've done, does that match up to the amount of marks that it's worth? Make sure you look after yourself mentally, physically. Don't spend your whole life studying. I know you kind of, it's crunch time a little bit. You're coming up to exams, so I know that it can be kind of tempting to just kind of hold yourself up in your room and do a lot of study. But try not to do that. Try to take breaks. Try to do other things as well. And with all of that being said, I think this is the end of our lecture for today. Thank you so much, guys, for having me. I will see you in the methods lectures if you come along to those. And I hope these are helpful. Good luck in your externals. I hope it all goes well for you.